Okay, so thank you everyone for joining this course, and we are really glad to have you all here. I see from the Google Forms that we have filled that most of the participants are either in advanced undergrad stage of their education, or they have already completed their undergraduate. So the level of this course, as I had planned earlier, was slightly lower than what is going to be covered now. So I'm changing the plan a little bit, that we will be covering some advanced topics like quantum Fourier transform and its applications to some of the problems, because that is a very important part of the quantum algorithm group that we have right now. So initially, I had planned it to be a little bit on the lower side, because we were thinking to target it to advanced high school or maybe early undergrad students. But since audience are mostly uh, uh, are having a background in engineering or science that is already advanced, so we'll be able to go much deeper into quantum computing. And my hope is this, that by the end of this course, all of you should be able to understand how quantum computers and quantum programs are different than the classical computers and programs, but also be able to understand some of the algorithms, and hopefully be able to develop and write your own algorithms and programs on quantum computers. So we'll be keeping the theory and some of the coding side by side. So towards the end of every lecture, I will be demonstrating some of the codes that can be run on IBM's quantum computer that we will be using for demonstration. Even though the theory and algorithm that we will be studying, it's applicable to other quantum computers that are available in the cloud, like the one from Google and Rigetti and IonQ, and a couple of other places. So during the course of this lecture, if you have any question, you can either type in the chat. But since we are not many people in this group, you can also just unmute yourself and ask the question right there as well. Mosana will be keeping an eye on the chat, and she will be prompting me for questions as well. I will also be taking, short breaks every 10-15 minutes, and be taking questions in that short break as well. So again, since we are going to plan to go a bit deeper, and from the Google Forms, from the educational backgrounds that I have, I might be assuming some of the things, especially in dealing with matrices, complex numbers, and a little bit of maths. But if you find anything that I'm using and you're not familiar with it, please do let me know, and I would be happy to explain. Okay, so let me share my screen and start formally. So before we begin, if there is any question on your mind that you have right now, please do ask regarding the course or how we are going to proceed in this course. Okay, so if there's no question, let me begin. So I'm going to begin by first introducing the contents of this course. So in this course, uh, I plan to start with an introduction to basics of quantum computers, like what are qubits, what are quantum computers, and how they are different from classical computers. We'll talk about uh, entanglement and teleportation. Sorry, my handwriting is, slightly not good on the screen. Hopefully, I'll be speaking along with it, so you'll be able to see what I'm writing. And it would get better when I'll be doing math on it. Okay, and then I will talk about how to think about quantum computer programs, because thinking about quantum computer programs is somewhat different than how we think about classical programs. For classical programming, our brains are sort of already tuned to it. For example, we already know how to tell, someone to do something. If I want, somebody to go to some, let's say, restaurant and bring some food, I will, tell him or her, okay, this is a money, take it and go on a car or some other vehicle and go to that stop, take this thing and bring it back and so on. So this, and if we have to write a program on a computer, it's almost similar to this, that we have a set of sequential instructions, and the computer implements them, and that's how classical programs work. But quantum programs are slightly different in thinking, and they're also different in implementation. So we'll talk about quantum programs, and specifically the circuit model for these quantum programs, and how do we implement different problems and algorithms using gates uh, in this program a quantum computer. So we'll talk about that. And then after about 2 to 3 lectures, once we have covered these basics, I will start with simple but uh, powerful algorithms that will explain right away why quantum computers are superior to classical computers. At least that's what we think right now, from the type of algorithms and things that we can run on a quantum computer than on a classical computer. And with these simple algorithms, and I will actually talk about particular two examples. One is the Deutsch Jozsa algorithm, and the other one is the Bernstein Vazirani algorithms. Both of these algorithms are not very practical in the sense that they don't do much practically for us, but they sort of explain the power of quantum computers right away. And with this thing, actually, we will also be able to understand how quantum programs work, and how to analyze them, and how to understand them. So once we have developed this basic facilitation with quantum algorithms, then I'll talk about two fundamental algorithms that have driven research in quantum computers. The first algorithm that we will talk about is Groover's search algorithm, that that seems to search through an unstructured database much more quicker than any classical search algorithm that searches through an unstructured database. So we will develop this algorithm, we will analyze it and implement it on a quantum computer as well, and we will know how it works. And then the second group of algorithms that we will discuss is quantum Fourier transform and its applications, for example, in finding the eigenvalues and of a unitary operator, which then has applications in factoring, let's say, composite prime numbers into its primes and so on. So hopefully, and we'll end the course after QFT and its applications. And by the end of this course, my hope is that you will not only be able to analyze the current algorithms that are out there, the basic algorithms, but also see why these algorithms are much faster than the known classical algorithms that we have available to us so far, and how we can use quantum computers to run these programs. I'll be showing example codes and explaining the codes to you as well, and we'll be giving out some of the assignments as well. And it would be optional for you whether you want to do those assignments or not. But if you do those assignments, I would be happy to provide you feedback on them if there is any trouble with them or if they're okay. And Okay, so any questions so far on the contents of the course or how we are going to proceed it?
Assalamu alaikum, sir. My name is Madiha Khalid, and my background is basically from information security. I'm actually working in information security, and these days I'm exploring the quantum computing factor in cryptography. So I would like to request that if you can please add an entanglement. BB84 and BB92 are slightly basic algorithms. So if you can add any entanglement-based cryptography algorithm in this course, that would be great help.
Okay, so Walaikum Assalam. Thank you very much for your suggestion. And we will definitely have one session on entanglement and teleportation. And a similar circuit is actually used for this quantum key distribution algorithm as well. And I will see that if we can include one short session on that as well. Thank you. Okay, so let's now begin, and let me share the plan for today. Today, I plan to have a general motivating discussion, plus a discussion that probably give you some understanding of classical versus quantum computer, that how do quantum computers work. Of course, my discussion is going to be very vague and perhaps not very precise in terms of physics, but given the background of audience that we have, that most of the people are not from physics background, I will not be able to be too technical, but still will try to give you some sort of an understanding of how quantum computers are physically implemented and how we think about programming them, and what does programming a quantum computer means. And once we have this basic discussion, then I will introduce the basic workhorse of quantum computer, which is a qubit or quantum bit. And we will develop notations and mathematical formalism to represent these qubits. And we will also then have a discussion about Jupyter Notebook, and I will run just a few lines of codes just to get you started, and also give you sort of introduction of how to work on Jupyter Notebooks. So after today's lecture, hopefully we will have a working knowledge of notations and some linear algebra, 2x2 matrices to work with qubits, and we will see how to take these concepts and implement them in Jupyter Notebook by the end of this session. Okay, so let me start with classical computers, which I hope that most of you are familiar with. So classical computers, they essentially work like this, that we have a memory, maybe a permanent memory or a temporary memory, in which we have bits. These bits are physical systems which can store information in such a way that the physical state of these bits tells us whether there is a 0 or 1 stored. For example, a lot of permanent memories are small domains of magnetic materials. So if, let's say, if this domain is magnetized in this direction, we can say that this is 1, and if this domain is magnetized in this direction, we can say that this is 0. And this small domain is actually made up of millions of atoms, maybe billions, if not more. And when we say that this domain is magnetized in this way, what we mean that most of the atoms, that the aggregate of the average behavior of magnetization is that it is magnetized this way. Or similarly, if it is, we say magnetized the other way, it means that most of the atoms are magnetized in this way. So, and even these memories work at room temperature as well, because at room temperature, the energy of excitation usually half times Boltzmann constant into room temperature, which is like 300 something kelvins. This energy is less than zero point 0.1 electron volt. So this is not enough to shift this domain, this magnetized domain. At most, this can shift around few atoms because of random thermal energy, but that doesn't make a difference. So that's why our error rate on these magnetized memories is very, very low. We might have error nowadays less than in 1 in billion bits, and we have codes to correct for that. So this memory is very faithful. So this is one part of the our classical computers. And then we have circuits, and these circuits are made up of transistors mostly. And let's say there are some transistor, and when we process this information, the circuit reads some of the bits from the memory, and these currents flow from here to this circuit, and then we have some outputs. And outputs, we can read it from its, let's say, voltage. If the voltage on the output is from 0 to, let's say, 0.5 volt, we will read it as a logical 0. And if the voltage is, let's say, between 4 and 5 volt, we can read it as a logical 1. And then we can store the information somewhere again. And inside, this box of processing unit, we have sort of physical flow of things, like currents are flowing from one side to the other side through different transistors, which are acting as control switches. Depending on the operation, the currents are directed from this way to that way, etc. And we can think about it in logical sense like this, that there are some inputs coming in, there are some, let's say, gate operations that are being performed on them, and then maybe something is combining like this. And so we can think about this classical computer as physically thinking that some currents are flowing through the circuit, and then logically it's a sequence of these logical gates. Because when the 0 and 1s, they are flowing through this circuit, we can work out what are the outputs are, and then we can design circuit that, okay, if we want this output, what would be the input. So there are a couple of features that make life easy for this classical circuit. One thing is that if we have one wire coming out, we can make multiple wires out of it. So this bit of information that is coming, it can be copied. It can go on this line and this line as well. Simply because physically, these transistors are connected to these DC voltage supplies. So if you need to have more current on certain line, more power is drawn from these batteries that goes into them. And similarly, we can terminate wires as well. For example, you can see that at the input we have more wires, at the output we have less wires. It means some of the wires have been terminated. So those terminations actually take place into the ground. So some of the power is dissipated into the ground. So this is how we think of classical circuit. It's made of transistor that we can imagine, laid in, let's say, in a plane, and the currents are flowing from one side to the other side. And similarly, the information is flowing from one side to the other side, and there are some of the operations that we are doing on it. Okay. On the other hand, the quantum computers are somewhat different than that. So in quantum computers, we have systems that are quantum mechanical in nature. That is, that we work with quantized systems. For example, just as an example, we don't have any quantum computer that uses this example, but I think this is very instructive. Let's consider hydrogen atom, because I think most people are familiar with hydrogen atom. So we know that hydrogen atom, we can picture it as a nucleus with a proton and an electron around it. So electron can be in shell 1, it can be in shell 2, shell 3, and so on. So I can make the energy level diagram like this. That maybe this is energy E naught, this is energy E1, E2, and so on. So if we imagine ourselves that the electron can only go in either shell, this energy E naught, the ground shell, or it can go to this first level shell. So we can picture this in our mind as a two-level system. That's when electron is in this state, we say that we have our bit. If we imagine this hydrogen atom to be a bit, our bit in zero state, if the electron is in the excited state, in the first excited state, we can say that our bit is in a one state, let's say. So we can work with this two-level system, and we can restrict ourselves to be always within these two levels, because we change the electron from one to another energy level by sending a photon of some frequency. So by restricting this frequency such that the energy of the photon is always the gap between these two levels, we will always be within these two levels, with the hope that none of the other two levels have the same energy gap. And in hydrogen atom, they don't. So it means that a quantum mechanical system that we work with is a multi-level system, but we select only two level out of that multi-level system to work with, and the mechanism that we have to transition our system from one level to another level is set up such that we only remain within these two levels. So our quantum mechanical system is this two-level system. We call this Q bit or a quantum bit. So a quantum bit is a two-level system. After these 10-15 minutes, we will always work with two levels. But right now we are talking about the physical system. So I'm saying that in general there are more levels, but we are only restricting ourselves to work with two levels. So this is called qubit. So the question arises that what is then the difference? Because classically also we have a system that is a two-level system, because these domains can be magnetized in either of the direction. It can be either this way or that way. So we have a two-level system classically as well. The difference in quantum mechanically is actually this, which is usually overlooked in elementary classes, that when we say that the electron can have energy E naught, this ground state energy, or electron can have energy which is equal to this level, but the state of the electron can have more than this. The electron doesn't have to be in a state which corresponds to the ground state, or the electron doesn't have to be in a state which corresponds to the excited state. Electron can be in a state which is a superposition of these two states. I don't have a physical way of picturing it or giving you a picture that what that state is, but there is something which you can imagine as an amalgamation of these two levels. We call it a superposition state. So the electron is in this superposition state. But when we measure it, what is the energy of the electron, we either find that it has energy E naught, or we find that it has energy E1. So this is different than the classical bit. The classical bit is physically either magnetized in one direction or it is magnetized in the other direction. So when it is magnetized in this way, we find it is to be in a state 1. When it is magnetized the other way, we find it to be in state 0. That's it. But quantum mechanically, in addition to these two possibilities, the electron can be either in the ground state, or it can be in the first excited state, or it can be in a superposition state where it's a state that when we measure its energy, there's a certain probability of it being in the ground state or in the upper state. We call this the superposition state. So this is how a quantum computer is different than a classical computer, really speaking. And we'll see that how we can use this superposition phenomena to do much more than what we can do classically. So how do we, let me give another example of implementation of the quantum computer, and then we'll see how we can how we picture logical operations with quantum system. So another possibility of the implementation of the quantum computer is, let's say, you can think of a spin. So a spin is something we call, it's a property of many fundamental particles, for example, electron. So we can think of hydrogen atom again, but let's say I now have a magnetic field applied as well. So I have a hydrogen atom, or maybe any other atom actually, in an external magnetic field. So an electron which is present in this level, it can have a spin up mean with respect to magnetic field, or it can have a spin down. And because of this, within this level, the energy of the electron is split in two parts. So energy can be this one, or it can be that one. So now we have a two-level system again. And remember, when I say we have a two-level system, I'm just focusing on this. That's why I'm saying it's a two-level system. In reality, the situation might be something like this, that my ground state is split into two levels. Let's say one of this state is also split into two levels, and maybe there's an upper state which is also split in two levels. But if I just concentrate on these, and what do I mean by concentrating? I mean that the electromagnetic wave that we send to manipulate the particle has frequency f. I use nu first, so let me use nu again. So the frequency nu of the electromagnetic wave is such that this h nu is equal to the gap between these two levels. So by restricting the frequency of our electromagnetic wave, we can focus on two levels. So we can make a quantum computer that works with these two levels. So actually, we do have an implementation of quantum computer which is called a trapped ion quantum computer, in which there are a bunch of atoms that are trapped inside some magnets, and by tapping them and accessing their energy levels, we can think of these individual ions as qubits. So this is one qubit, this is other qubit, this is other qubit. So I have like these 6 qubits strong. So these are essentially 6 ions, and I can work with each of these qubits. And there are ways of making multi-qubit gates and individual qubit gates. Single qubit gates are those operations which happen only with one qubit, and multi-qubit gates are operations that happen on combined qubits, on more than one qubits. So this is one implementation. Another implementation, which is actually the one that we will use in this course, the quantum computer that we will be using by IBM and also by Google, it's actually based on superconductors. So basically, you have something like this, that let's say you make a transistor by a conductor, which is this long conductor, and then I make a capacitor, and let's say we connect them. And this is actually made by aluminum, and this is an inductor L. So this is a capacitor C. So this becomes an LC resonator. So this is a familiar classical circuit. This is an LC resonator. But if I cool this LC resonator to a small temperature of, let's say, 10 power minus 3 Kelvin, and at this temperature, the energy of this resonator is so low that this becomes a quantum mechanical oscillator. So a quantum harmonic oscillator, if some of you are familiar, have energy levels that are like this. They're actually equally spaced energy levels. And this aluminum is a superconductor at this temperature, which means that that there is not going to be any resistance in this circuit, and this is sort of going to be a perfect resonator. But this has this one big trouble, that all of these energy levels are equally spaced. So whatever frequency of the waves that I take, if I restrict myself to these two levels, when my, let's say, system is in this level, I send an HF pulse to transition it to this downward level, it can go into the upper level as well, because this HF is the same gap as between these two levels and these two levels. So to make the gap between these two levels different, what people have done, they have introduced a Josephson junction, that they have made this gap very small and put an oxide layer here. Now this becomes a Josephson junction, which is essentially a nonlinear uh, diode type thing. So overall, now this becomes a nonlinear circuit, which means that our energy levels are now like this, that we have big difference here, slightly smaller here and smaller here. So now I have an energy gap, which is different than the other levels. So with this way, people have constructed this two-level quantum system. So again, remember, this is not really a two-level system. It's a multi-level system, but the energy level difference, the energy difference between different levels is different. And we focus only on this, these two levels. So this becomes effectively a two-level system. Okay, so just to say a couple of things about this, temperature. People work at this low temperature, not only because aluminum is a superconductor at less than 1 Kelvin, I think maybe 1 or 2 Kelvin. So it's a superconductor at a very low temperature. But there's another point, and that point is that we have to house this quantum circuit in an environment where, so let's say this is my this two-level system, this qubit. We have to house it at a place that nothing from the environment is coming, that there's no interference, because this is a very small system. So its energy difference is of the order of much less than actually electron volt. This frequency F is in microwave region. So 10 power 7, 8 hertz. So this is a frequency in microwave region. And even our room temperature is like 207, 300 something Kelvin temperature. So at room temperature, we have a lot of microwave noise. And not only that, actually, the microwave background radiation of the universe, they have a black body temperature of about 2.75 Kelvin. So this circuit is so sensitive that even the microwave background radiation that are present in the universe, everywhere in the universe, they are also too much for this circuit. So we have to go to a temperature which is even less than this universe background black body temperature as well. So that's why even if we use a superconductor, a material which is superconductor at a much higher temperature, we are still going to work at this very low temperature, simply to avoid noise from the environment. So when we go to this temperature, then the noise from the environment is negligible in this range. Okay, so let me stop here and take any question that people have about how do we picture a quantum computer, what a quantum computer is. Okay, so if not, then let me proceed ahead and give a summary. So in summary, a quantum computer is a two-level system. So let's say our low level, when the system is in this state, we say it's in state 0, and when it is in state upper state, it is in state 1. But practically, physically, these are actually just two levels out of many levels available in the physical system. And usually these quantum computers are cooled down to very low temperatures to insulate them from the environmental noise. And let me now discuss this physical property of quantum system, that the system cannot only exist in this state or this state, which corresponds to 0 or 1, but it can also exist in sort of a superposition state, that when we measure it, it either collapses to ground state or to this excited state. So this existence of the system in superposition state is actually what we harness in quantum computers. Okay, so let's now see how do we process information in quantum computers. So logical operations. So logically, what we do is it like this, that if you imagine your system to be like this, let this say this is a qubit. You can picture it like this. This is a two-level system. This is a two-level system. So quantum mechanical operation or logical operation on these quantum computers correspond to these type of operation that you, let's say, first prepare your system in the ground state, and then you send a pulse of light that has an energy equal to this gap, and your system goes to the upper state. Or we can send a pulse, continuous Rabi pulse for a certain amount of time to take the system into a certain superposition state. And that superposition state is sort of somewhere in between these two levels, that when we measure, the system collapses to one of these two states. So these logical operations, we can represent them like this. Let's say we have one qubit, so we do some operation, and then we do some other operation, and then we do some other operation, and then we have a certain state prepared of this qubit. Similarly, we might have another qubit in parallel, and we do something on that and something again, and then we have that qubit in a certain state. We might have another qubit, and we might do a certain operation on it depending on the state of this qubit, and then we have a certain output. So one important feature of this circuit is this, that the number of inputs and number of outputs are exactly the same. Because during our quantum mechanical processing, we are not destroying any atom or any LC resonator that we have prepared. So physically, every qubit is over there. You measure it or not, that's your choice. You do something with it and then you don't measure it, that's your choice. But physically, all the inputs are equal to the number of inputs are equal to number of outputs. So this means our quantum computers are reversible, because we know the number of inputs, and we'll see shortly that the operations are also of a certain kind. So from since the number of outputs are equal to number of inputs and operations are only going to be of certain kind, then we can reverse this computation as well. So quantum computers are reversible as opposed to classical computers. And then there's another actually very important property of quantum computer, and that is that if you have a certain system prepared in some state, you cannot copy it. So let's say this system was in certain state. You cannot have a system which is exactly in the same state and you still keep this. You can copy this qubit into another qubit, but you will destroy your original qubit. And there's a simple reason, and that simple reason is the measurements. Because when we do measurements of these fragile systems, these measurements disturb the system. Only in special cases, we are able to mimic the qubit. For example, if your qubit is already in the ground state, it is in level 0, you measure it, it is in 0 level, and then what you can do, you can prepare your other qubit in level 0. So both of these qubits are 0 level. Or maybe your system was in level 1. So when you measure it, it was there, and then you prepare your other qubit in level 1 as well. So in these two special cases, you are able to prepare a copy of this qubit. But if your system is in some superposition state, so in such a way, let's say it has a 30% probability of collapsing to your level 1 and 65% probability of collapsing to your level 0. Now, when you measure it, it would have collapsed to either 0 or 1. So once it collapsed to this 0 or 1, you have no idea what was the state, because when we measure 0, we can say that there was this much probability of its collapse to this thing. So in that case, we are not able to make any copy of it.
Hi,
So,
sir. I have two
Jiri?
questions. I have two
Mhm.
questions. My first question is, if we have all the history of operations that we do on specific qubit, then by mimic all these operations again, can we not make exact copy of that qubit?
Yes, we can. So the question is that, let's say we start with 2 qubits in a certain initial state, which is exactly the same. Let's say they both are in ground state, in 0 level, and we then do a series of operation, some operation U1, U2, and we do exactly the same series of operations on another qubit, which is essentially started in exactly the same state. Of course, at the end of this, they would both be in exactly the same state. So this is,
Sure.
we call preparing identical copies of a system.
Sure. Sir, the second question is, whenever we measure the qubit, we found it in zero or in one state. So how can we confidently say that this was in superposition when we did not measure it, or it is because we have mathematics behind it that that bring confidence in us that we can say that it was in superposition when we was not measuring it,
So
because when
okay, so sorry to cut you out, but I think I understand your question. So it's a brilliant question. So your question is that how do we know that the system is in superposition state? We do, we know it exactly from these types of things that you just said. Okay, if I prepare two systems in two identical states, and I measure it. I measure this one, and let's say I get 1, and I measure this and I get 0. So this is a proof right away that the system was neither in 1 nor in 0 state. It was in some superposition state. That's why I got it into different measurement. But of course, these are just two measurements. It is possible that they both collapse to 1. So the way to find the superposition state is that we prepare a lot of copies of identical copies of this system, and we do measurements, and then we count the number of outputs. So if, let's say, we did 1,000 measurements on identical copies, and for all 1,000 we got only one as output, so then we can say with some confidence that this state corresponded to a state which is not a superposition state, but it's only state 1. But if we, let's say, out of 1,000 measurements, we got 30% of time ones and 70% of time 0, then we can say confidently that the system was, this system is in superposition state. Okay?
sir, I'm clear. Thank you.
Okay, good. Excellent. So any other question? Okay, so let me now talk about the quantum computer programming model. How do we prepare, how do we construct algorithm, and how do we analyze them? So for this, the most famous model is actually a circuit model that most people use to illustrate the series of steps. And the model is like this, that you specify the operations on qubits using different symbols for different operations. For example, we can say that we perform some gate X. I'll explain what this gate is, and then some gate H and some gate Y, and this qubit went to this state. So this has an advantage that this mimics sort of our classical circuit model. So there we have our AND, NOT, XOR, etc. gates, and we picture them like this. So similarly, this model is almost like that. But there is one difference, that physically, it's not really mimicking the classical system. In classical computer, as I said earlier, that something is flowing through a circuit. So our logical circuit sort of tries to mimic that. But now in quantum computer, our qubit is sitting there, and we are performing different operations. And those operations are really electromagnetic pulses of different durations and different shapes. That when, let's say, just for advanced people, that electromagnetic waves, they're like, if we picture the plane waves like this, so these different operations correspond to if we started at 0, or if we started here, or what phase we started our pulse with, and how long the pulse was sent to drive this two-level system. So this amounts to different types of operations that takes our qubit from one state to another state. So we show this series of operations using this sequence of gates. So this gate model is something that we are going to use. And these gates, so we will use the word gate, but they're not those classical gates. They are operations. But we will, from now on, almost be thinking about them as those sort of gates. So there are a couple of things that we have to keep in mind. One thing is that you cannot make one wire into another wire. You can't do like this, that, okay, I take and one input goes there and one input comes here from this line. So this is not allowed. So this fan out operation is forbidden, because we cannot make a copy of this qubit into two parts without destroying it. Remember, when we started our qubit in a certain state, we know what state it is. But once we are performing different operation, it's going into superposition states. So in general, we don't know what state is, and we cannot make a copy. So which means that we cannot draw this line from here. So the sequence is going to be like this. The number of inputs are going to be equal to number of outputs, and there's no fan out going to be there. We can do swap. For example, you are doing some operation on this qubit, and you then sort of, there's another qubit, you do some operation. So you can do this swapping physically. For example, physically you have a qubit here, you're doing something here, and you're doing something here, and maybe you want to do some coupled operation on these two, but your hardware doesn't allow that. Okay, your hardware might be designed that you can only do coupled operation between these two, but your algorithm is such that you want to do coupled operation on these. So what we can then do, we can do a swap without measuring them, and that swap usually happen through other ancilia qubits, that we first copy this qubit into this one, this gets destroyed, so this is destroyed, and then we copy this one into this one, and then we copy this one back to here. So but when we copy from here to here, this gets destroyed, and we will derive a circuit to do that. So we can do this swapping, but we cannot do fan out. So this is one important thing. Another important point that we have to keep in mind for these quantum circuits is that all operations are unitary, and we'll say much more about it, that why it is the case. This is basically to preserve probabilities. Okay, so all of these operations are unitary, and which means that the probabilities must be conserved. For example, when we have a system like this, and we say the system is in superposition state, that there is some probability of it collapsing to 1 and some probability of it collapsing to 0. Note my language. I'm not saying that system is in a superposition state, that it has some probability of being in state 1 and some probability of being in state 0. That's not what I'm saying. I'm saying it is in a some state, which when we measure has a probability of collapsing to either 0 or probability of collapsing to 1. Before we measure, it's in neither 0 nor 1. It is in a superposition state. Okay, but the total probability should always be 1. That if it has 30% probability of collapsing to 1, it should have 70% probability of collapsing to 0. So the sum of probabilities should add to 100%. So to preserve this property, if I represent my input state with psi ket, so this is Dirac notation. I will shortly introduce it formally, but we represent these states with this funny looking way of this straight line, vertical line, and then this alligator mouth. So we put some symbol here to denote some state. This is called Dirac notation. So if we have some state psi that goes to some state psi prime after some operation u, we need to preserve the probabilities, and that can only happen if this u is unitary. Let's see how. So we get psi prime as u psi. So this u operates on psi, and we get psi prime. And to conserve its probabilities, I'll actually prove it a little bit later when I introduce the Mayer, how to find the probabilities, etc. So to conserve these probabilities, this u has to be unitary. Let's postpone this unitary business a little bit after I introduce the Dirac notation formula. So let's actually introduce this Dirac notation to represent state. Okay, so now we are down to this business of imagining that our quantum computer is a two-level system. It's a quantum mechanical system. So let's represent the one state of the system with this zero ket. It's called ket. And the system in upper level with the state one ket. So this is one ket, this is zero ket. Now instead of 0 and 1, I'll be using ket notation. And in general, our general state psi can be, in some state psi. So since this is a two-level system, we can introduce 2x2 matrices to represent these states. So in general, we represent our state using these 2x1 matrices, and such that, and this is important, that A1 absolute square plus A2 absolute square is 1, which means that the states are normalized, because this A1 represents the probability, A1 mod square represents the probability of the system collapsing to one state, and A2 represents the probability of collapsing to another state. Okay, so this is a state psi represented by this 2x1 matrix. And its magnitude is, we can represent the magnitude like this. It's A1 square, A2 square. And to make people's life a bit easier, people have introduced another way of writing this magnitude and finding this magnitude, because we are going to do it again and again. That we define another symbol. Now this is called a bra. So this is a bra psi, which is nothing but a conjugate transpose of this state. So this symbol, which is the symbol of cross, this is representing a conjugate transpose of this matrix. So which means that if you have A1, A2, its conjugate transpose would be, you take conjugate of each of these and then you take transpose. So transpose mean this column becomes a row. So now this is a row matrix, and this psi is a column vector, and I can write this magnitude square as psi. So this is nothing but the magnitude of psi. So this is this vector, and this psi ket is this column vector. Now if we multiply these two, I get A1 star into A1 plus A2 star into A2. And we have only one element, we don't draw the matrix symbol. So this is nothing but A1 modulus square and A2 modulus square. So this is the magnitude square of this state psi. And we require it to be 1 always, because A1 square is the probability of finding the system in one state, and A2 square is the probability of finding in another state. This normalization is the requirement to make sense of everything we do in quantum physics. Okay, so let's now introduce, let me give a couple of examples first. Suppose I have this state A as 3, 4 iota. So let's see if this is normalized state or not. So for that, let's find out this Bra vector. So this would be its conjugate transpose. 3's conjugate is 3, 4i's conjugate is minus 4i, and when I take its transpose, this becomes this vector. So its magnitude square would be A into A. This, by the way, is called inner product as well. So this is inner product of this Bra vector and this ket vector. So 3 minus 4i, 3, 4i. So 3 into 3 is 9, minus 4i into 4i is plus 16, because I square is 1, and this I is iota. Iota is, so this is minus 1. Iota is minus 1 square root. So minus 4i into 4i is minus 16 iota square. So iota square is minus 1. So this minus becomes plus, and this is 25. So it means that this state is not normalized because its magnitude square is not 1, it's 25. So how do we normalize state A? We simply divide it by the square root of this number. So let's make the first number as 3 over 5 and the second number as 4 over 5 iota. Note that in quantum physics, we require complex numbers to donate these states. Okay, so any question about this bracket notation? Perfect. So let me now introduce a concept of basis. Well, this is basic stuff, so I apologize if somebody is a bit advanced and they find it boring. I'm trying to make it inclusive so that everyone who's completely new also is able to get this stuff. So let me introduce this concept of basis. So a basis, if I define it more rigorously, it's a set of vectors in a vector space that is enough to represent any other vector in that vector space. For example, if we talk about this two-level quantum system, I can represent this state psi which was A1, A2 like this, that A1 here, 1, 0 plus A2 into 0, 1. And we can identify this 1, 0 vector with 0 and this 0, 1 vector with 1 state. So this psi state, which is a general A1, A2 state, I have now written it as a superposition of 0 and 1 because there is some A1 and some A2. And this 0 and 1, this is called the basis of this two-level systems vector space, because I can represent all states. You can have any A1, A2, they can all be represented as a weighted sum of 0 and 1 vector, where 0 is this 1, 0 and 1 is this 0, 1 vector. So this basis has actually a special name. It's called computational basis. And now we have a better idea of this A1, A2. So this A1 is actually proportional to the probability of measuring the system in state 0. And this A2 gives us a measure of probability of finding system in state 1. So more precisely, if we have a system in certain state psi, which is a superposition state. So when we measure this state psi, the probability of measuring this state psi such that the system is collapsed to the zero state is given by the A1 mod square, and probability of the system collapsing to one state one is given by A2 mod square. So now we have this physical significance attached to this A1 and A2. A1 mod square gives us the probability of system collapsing into state 0, and A2 mod square gives us the probability of system collapsing to state 2. And this mod square is nothing, or we can also call it absolute square, is nothing but A2 into A2 star, and A1 mod square is nothing but A1 into A1 star, that you multiply the complex number with its conjugate. Okay, so any question so far, or comment if we are going too low for some people?
I'd like to read out a comment. Zahoor says that you're doing excellent, very much interesting and important for beginners. So yeah, that's good.
Okay, good. So it means we are okay. Another?
Yeah, he says so. Madiha Khalid had asked a question sometime earlier. She says that can we say that gates vary the spin of electrons?
If she means by varying, let's say its orientation, so we can and we cannot. You know, picturing quantum mechanics is a very hard job. So for example, when let's say we have a two-level system and we can equate it to a spin of electron. So spin, I don't know, it could be oriented at some angle, but let's say if we have prepared it such a way that there's an external magnetic field, and whenever I measure it, its component along z is always in this direction. So we can say that the spin is oriented in this way. And if we measure it and it is found in this way, we can say that it is oriented in this way. But that's not all that can be done. It is the same thing that if I measure my quantum mechanical system, another two-level system, that if it is in this level E naught, with energy E naught, let's say it's in zero level, okay, it can be here. And when it is in upper state with energy E1, let's say it's state 1. But that's not all that is possible. The superposition state is also possible. And we were going to picture it in terms of rotations when we go to visualization. But these are just mechanical and artificial visualization that we have prepared to sort of understand. Physically, we can't say that there is a spin that is, rotating like this. We unfortunately cannot assign any picture to that. Though we'll be studying Bloch sphere, which is an artificial mechanism prepared by us to sort of, visualize these things so that we can develop some intuition of working with the math. The reality is actually only this, that we have a system in superposition state. Okay, let's say some 3/4, 3/5 plus 4 iota over 5, 1. So when we do some operation, this goes to another superposition state, which let's say goes to some other state. So these B1, B2 numbers, are there. But there's no physical thing probably in terms of rotation that is happening. We can't imagine that, even though we will study an artificial mechanism of visualization.
Thank you, sir. I'm so sorry. I have a small question. You refer to as X basis as the computational basis. So is this sort of a standard that we assign the name of computational basis to X basis only? Can we assign this specific term to Z basis or Y basis, or is this specifically for the X basis?
So it's specifically for the 0, 1 basis that you are calling X basis, because of the reason that they are, eigenvectors of the X operator that we will study. But this computational basis name is reserved for the 0, 1. That's how most people use it.
Thank you, sir.
Thank you. Okay, so we can have actually other bases as well. So for example, we can construct a basis of basis vector plus and minus. So first of all, you can check that these basis vectors that I have selected, they are normalized. For example, if I find its magnitude square plus with inner product with plus, so this would be 1 over under 2, 0 plus 1 into, and it, I don't have to take conjugate because this under root 2 is a real number, multiplied by with the plus vector itself, 0, 1. So 1 over under 2 into 1 over under 2 is 1 over 2. This 0 into 0, 1 into 0, and then 1 into 0 plus 1 into 1. So let's evaluate this 0 into 0. So this 0 vector is 1, 0. So its magnitude, its 0 dot 0 is 1, 0 into 1, 0. So 1 into 1, 1, 0 into 0. So this is 1. And if I find this inner product of 1 and 0, so this 1 is 0, 1, 0 is 1, 0. So this is 0 into 1 plus 1 into 0. So this is 0. So it means that this number is 0. Similarly, this is 0. So this 1 is also normalized. So this is 1. So I get this inner product of plus and plus as 1 over 2. This is 1 plus 0 plus 0 plus 1. So 1 plus 1, 2, 2 cancel with 2. So this is 1. So it means that this plus vector is normalized. Similarly, you can check that this minus vector is normalized. And I would strongly encourage you to work out this plus into minus product, and you will see that the answer is 0. Okay, so this is also another basis. This is referred to as plus minus basis. It also has another name that we will talk about later. Okay, and there's actually another basis plus iota minus iota basis, but let's leave it out. So let's now come to this question about visualization. How to visualize our qubit? Because that's a hard thing to do, and it's needed to develop intuition. Because working with maths is precise, and we can always do everything, but it takes a lot of time and more imagination to develop intuition just working with equation. So people have developed ways to visualize these qubits. If our qubits and their superposition, weights were real, our life would have been a lot easier. If it would be real, I could represent, let's say, any state A1, 0, 1, A2 in just a plane. That you can have, let's say this is 0 axis, this is 1 axis. So any state psi can be represented by a vector. So its magnitude along the z is this component A, and its magnitude, the magnitude of its projection onto state 1 is A2. So this is a lot easy. And by the way, in the same sense, you could picture the other bases. So this, let's say, you can imagine this plus bases, plus minus bases with these two orthogonal vector, and then the projection of this psi vector onto this one would be some B1, and its projection onto this vector should be B2. So we can write the same as like this. Okay, but life is not easy because this thing is not possible because A1 and A2 are complex numbers. Still, some people, like to imagine it like this because 0 and 1 are orthogonal to each other, and plus and minus are orthogonal to each other, and so on. So you can perhaps initially visualize it, but that doesn't give us a complete picture. So what we have to realize is that A1 is a complex number. So something like 2 plus 3 iota divided by 2 square plus, sorry. So it is some complex number, let's say some a1 dash plus iota a1 double dash. So similarly, our a2 coefficient is also complex, some real part and some imaginary part. Okay, so it means we require 4 parameters. We have 4 parameters to that spans this state psi, general state psi. However, since a1 mod square plus a2 mod square is 1, we have this constraint, which means that instead of 4, we only have 3 parameters. So we need a way to visualize this state with 3 parameters. And let's see how we can do that. And since our states are normalized, I can exploit this normalization. And let's first write that, let's say A1 is some R1 iota alpha 1. I can write any complex number in polar form with its magnitude R1 and exponential iota alpha 1. This exponential iota x is cos x plus iota sine x. Similarly, we can write A2 as R2 exponential iota alpha 2. There is some phase alpha 1, some phase alpha 2. These R1, R2 are real positive numbers because they are magnitudes of these complex numbers. So these conditions that A1 square plus A2 square should be 1, this gives us that R1 square plus R2 square should be 1, where R1 is a positive real number, R2 is a positive real number. Similarly, we can substitute this A1, A2 in state psi, but let's first do something here. So we have this equation with 2 parameter R1 and R2, which are constrained in this way. So one way is that we imagine that this R1 is equal to some cos theta by 2 square, and this R2 square is some sine square theta by 2 is equal to 1. Now, instead of 2 parameter R1, R2, I only have 1 parameter theta, which can actually represent both of these numbers, simply because these are not independent. So R1 square is equal to 1 minus R2 square. So all I have to do is specify R2. And once I specify R2, R1 is known. So it means I only need 1 parameter to specify. And one way to do that is that I specify this R2, identify with some, let's say, sine theta by 2. There's a reason for doing it sine theta by 2 instead of theta. And I'll see a little bit later why. And I can also see quickly that there's a constraint on R1 and R2. R1 and R2 has to be between 0 and 1, right? Because if one of them is greater than 1, this condition cannot be satisfied. So it means I can represent them with the sinusoidal function. So that's why I was able to identify R2 with sine theta by 2. And I did it with theta by 2 because now my theta by 2 has a range that it can go from 0 to 180 degrees. 90 degrees. Because R1, R2 is 0 to 1. So theta can, this number can be 0 or 1. So when it is 1, theta by 2 is 90 degree. So it means theta by 2 can go from 0 to 90 degree, or theta can go from 0 to 180 degree. So this is a constraint on theta. Let's now see another way, how to work out the other parameters. So our psi was A1, 0, A2, 1. And let's substitute for A1 R, exponential iota alpha 1. For A2, R2, exponential iota alpha 2. And I can take exponential iota alpha 1 common. So we are left with R1, 0 plus R2 exponential iota alpha 2 minus alpha 1, 1. Now, this can further be written out like this, exponential iota alpha 1. Instead of R1, we can write cos theta by 2, 0. Instead of R2, I can write sine theta by 2. And let's define alpha 2 minus alpha 1 sum phi. Now this phi is, alpha 2 minus alpha 1. Now in quantum physics, this number, exponential iota alpha 1, doesn't feature in measurements, okay? It does define a unique state. You have different value of alpha 1, you have a different state. But in measurement, it doesn't play a role. Because when I multiply this psi with the, let's say, conjugate of itself, this goes away, okay? Because if we have this psi to find, its magnitude, this will go away because when I multiply it with the exponential minus alpha 1, it will go away. But not also that, if I want to find what's the probability of measuring 0. So probability of measuring 0 is the projection of this psi onto this 0 state. And the way to do this, that I multiply with this 0, this state psi, and when we do this psi multiplication with this one, we get this exponential iota alpha 1 cos theta by 2, 0, 0 plus exponential iota phi sine theta by 2, 0, 1. But 0 into 1 is 0 because there are orthogonal vectors. So this term go away, and 0 into 0 is 1. So this is 1. So I'm left with exponential iota alpha 1 cos theta by 2. And now to find the probability of measuring this 0, I have to take mod squared. So when I take its mod squared, I'm only left with cosine squared theta by 2. So this exponential iota alpha 1 doesn't figure out in probability of measuring the state 0. So that's why in our representation, we can ignore this. So if we ignore it in representation, we are left with our state with only two parameters, theta and phi. Where theta goes from 0 to 180 degrees, and phi goes from 0 to 360 degrees, or 0 to 2 pi, because if we come back here, phi was alpha 2 minus alpha 1, and alpha 2 is phase here, alpha 1 is phase here. So in general, alpha 2 and alpha 1 can both be from 0 to 360 degrees or 0 to 2 pi. So it means that this difference alpha 2 minus alpha 1 can be anywhere from 0 to 360 degrees. So we now have a state which is characterized by two parameters, theta, which goes from 0 to pi, and phi, which goes from 0 to 2 pi. And people do it on something which is called a block sphere. So I noticed that I'm running little bit late. So do you want me to complete it, or should we stop?
Please complete it, sir.
If there is anybody who has to go. If not, I promise I won't take more than 10 minutes. Okay, so it means that I can represent this state on a surface of a sphere. This sphere is called block sphere. Using spherical coordinate, let's say this is x-axis, this is y-axis, this is z-axis. So if I have a general state psi, from this state psi, I should write it in this way and then find theta and phi. And using this, I can represent this state here. So this theta is the angle with the z-axis, and phi is the angle of this projection in the x-plane. So this is the angle phi. So you project this vector into xz plane, and the angle of this projection with the x-axis is phi. So as an example, this zero state. So if this zero state I can write as 1 into 0 plus 0 into 1. So it means that this theta has to be 0. Because if theta is 0, this cos 0 would be 1 and sine 0 would be 0. And phi doesn't matter because when sine 0 is 0, whatever phi is, this number is going to multiply with 0. So it means zero state is a state with theta 0. So it can be represented like this. Similarly, one state, which can be written as 0 into 0 plus 1 into 1, should have phi 0 and should have theta as 180 degrees. Okay, not 90 degrees, but 180 degree, because when I divide 180 by 2, I will get 90 degree and sine 90 is 1. And cos 90 would be 0. So it means, so this state has to be represented by this vector, because this is a vector that has theta 180 degrees, and phi is 0 for this. Similarly, if we talk about the plus state, so plus state was 1 over under root 2, 0 plus 1. So it means it's 1 over under 2, 0 plus 1 over under 2, 1. So cos theta by 2 and sine theta by 2 both are 1 under root 2. It means that theta by 2 should be 45 degrees and phi should be 0. Because you see, there's only 1 over under root 2 here. There's no other number matches multiplying here. So phi is 0 and theta by 2 is 45 degree, which means theta is 90 degree. So this is a state which has a theta 90 and phi 0. So this is a state like this. So this is the plus state. Similarly, you will see that the minus state is along the negative x-axis like this. Okay, so this is how we can represent states on the block sphere. Any question so far? So let me, in 2-3 minutes, just introduce you to using Jupyter Notebook to start writing programs for quantum computers. I will send out this file to all of you. So only few lines of code just to get you, started on this one. So let me first share my computer screen. Okay, so let's open Jupyter Notebook. Those of you who have not yet installed Jupyter Notebook, or they might face some trouble in installation of some packages, there is a very good thing available on the web. It's called Google Collab. So just type in Google Collab, and you go to this first link, Google Collab, and you get exactly the same thing. So here, let's say you start with a new notebook, and when you do that, okay, so you will reach this point, and this will work exactly the same. The only thing is that you will have to upload everything to the cloud to work, and your notebooks would also be here. But anyway, so let me start with this thing. You click on this button, upload, and the notebook that I will send to you, you can upload it here. Let's overwrite and lost modified. Okay. So this is how Jupyter Notebook will open in front of you. You first have to install this package Qiskit, which is Quantum Information Science Kit, developed by IBM people. So you can install it using this command pip after this exclamation sign, install Qiskit. So I have already installed even, and to run it, you press Shift and Enter together, okay? Or you can click on this button, run right over here. But Shift Enter is quick. So you press Shift Enter, you will see all of this thing in front of you. And once you install everything, you will reach on this point. And just to verify if you have installed Qiskit correctly, you should use this command that from Qiskit, import this package quantum circuit. Let me shift run it. As long as this star appears here, it means that the notebook is still running. Okay, so this command has run. And now you see that I'm recalling this command plot block multivector from this package Qiskit visualization. So in Python, which is being used as backend at the backend of the Jupyter, you actually have to import most of the functions before you're able to use them. By default, only a very limited functionality is available. So for everything that we have to use later, we first have to import it from somewhere, most of the time. So from this Qiskit visualization package, I imported this command plot block multivector. And now I define my sum state 0, 1, and then I am using this command plot multi-block vector sum state. And you see this 0, 1 corresponds to 1. So when I press Shift Enter, it plots it on the block sphere. Now we can do general stuff. So for example, for that, I will need this package numpy. It has operation for square root and for many math functions. So what I'm saying that import numpy as np. So any function in this numpy package will be used with np dot extension. So let's say I have this number a plus 0, 2j. This j is a symbol for iota in Python. And once I have this a, b, I compute this magnitude. So this magnitude is square root of absolute a's square. Remember, for power in Python, you use double star, not single star, and not the hat symbol. So similarly, for this absolute b square. So now once I computed this magnitude, I defined this state 2, which is a by mag, b by mag. So this is sort of normalization of this state. And then I can use this thing. Now let's see, we can have, so this is state 2. So I should type state 2. Okay, so you see this state is being plotted. And if you want to change this to some 1, so you can specify this state, and this command plot block multivector, this can show your states on this block sphere. So here's another way of defining the states by using NumPy arrays, but that's not really needed. I see there are a couple of perhaps things popping up in the chat. Is there any question there?
There's no question.
Okay, good. So the last thing is that if you want to, let's say, initialize some qubit. So the way we program in Qiskit is that we define a quantum circuit and we specify the number of qubits. So I'm defining a quantum circuit QC with 1 qubit, and then I'm initializing this qubit with state 2. And in Python, the indexing starts with 0. So if you have like 10 things, the indexing is 0, 1, 2, 3, and so on. So since I have only 1 qubit in my quantum circuit, I'm saying that with state 2 vector, initialize this qubit 0. And then qc.draw just draws my circuit. So let's define this state 2. And when I execute this command, this is sort of the drawn out version of this quantum circuit. So I'll send it out this notebook to everyone, and you can practice it at home. Any questions on this notebook or anything else?
Sir, any material regarding this lecture to read recommended by you?
There's really not any material that is this basic. But once we get a little bit advanced, then there are actually a lot of books, there are PDF and lecture notes available on the web that you can search for. Okay, so thank you very much. I hope that it wasn't, too boring for some of you who already have introduction, and it wasn't, too high for those of you who are new. But if you have any question or suggestion, you can send me an email. I think there's a question from Nard. Yes, Nard, please go ahead.
When I opened the Jupyter website, there was two versions, like Jupyter Lab or Jupyter Notebook, and you can choose whether to download the lab or the notebook. Should we notebook?
Okay. Yes, go for notebook.
Thank you.
Sure. Okay, and we will be sharing the recording as well. Mohsen, I think, will be doing that.
Yes, it might be done in the morning, but we will definitely share it as soon as possible.
Okay, then, so see you tomorrow with perhaps something more concrete. Thank you.
Thank you, sir. Bye.